Let's move on now to defining the proposed case photovoltaic array. Moving from the inverter battery form, we go to the base load photovoltaic system here. So this is where we can define the base load power system, that is the principal power system, as opposed to the peak power system, which is used when the base load power system is unable to provide power. And of course, we want a photovoltaic system here. So our first job is to indicate the slope and the azimuth of the photovoltaic array. You might recall that on the location page, we selected our location and it provided us climate data for that location. And here is the daily solar radiation on the horizontal for that location. The first number for January is 1.91 kilowatt hours per meter squared per day. That's in the horizontal. When I go back to the energy page, I see that same number. That's the daily solar radiation on the horizontal. These numbers are coming directly from the climate database. Unfortunately, these are horizontal numbers. We want them to be for an array that's got an arbitrary orientation. It might actually be in a moving array as well. It could be a single axis, two axis, or azimuth tracking system. I'm going to assume that it's a fixed orientation. Perhaps it's on the roof of the off-grid home, and in which case we'd look at, say, the azimuth of the roof, that is the direction that the roof faces, and then the slope of the roof plus any additional tilt that we might add through a structure. The azimuth is defined with 180 degrees being north and south being 0. That's opposite the convention of a compass, but is the convention adopted in ret screen, largely because in the northern hemisphere, where this software originated, most arrays are going to face the south because that's going to maximize their electricity generation. So we're going to assume that there's a south-facing roof that we can put this on, so I'll put in 0 there. And then based on that, we can adjust the slope and see what impact that has on the tilted solar radiation. So if I put in, for instance, a vertical south-facing array, I'll see that this does a lot to improve the solar energy impinging on the array during the winter months. We see that compared with the horizontal, there's much more solar energy available during the winter months. However, during the summer, the opposite is true. So that would be the case for mounting on a wall. If we put it on the roof, maybe the roof is at, say, a 20-25 degree slope. Maybe we can tilt these up a little bit. So let's say we get this to 30 degree slope. That should allow some snow to run off it as well. So I put this at 30 degrees and I see that overall the impact is not so strong in winter now, but I still get lots of solar collection during summer. Obviously, if the load is not changing over the course of the year, the critical months will be the winter months. We would favor having a higher slope here, and if we were doing ground mounting, that's maybe what we would do. But if we're doing roof mounting, we may be restricted by the practical considerations of mounting this on the roof. So I'm going to leave that at 30 for now. Currently, the fraction of load being delivered in each month is 0, and that's why we get these warning signs. Of course, that makes sense. We haven't told ret screen what size photovoltaic array we have. So we'll do that next. The photovoltaic array type refers to the technology we're using, and we have a range of choices there. That mainly is used by ret screen to estimate how high or low temperatures affect the module performance. I'm going to leave it on monocrystalline silicon here. For the power capacity, I'm going to leave that blank for now because I don't know what it is. I'm going to select the power capacity in order to meet the specified load in all these months. But in order to do that, I first have to set up the rest of the parameters here. So for efficiency here, it's not a critical parameter except in that it determines what the solar collector area is. So I'm going to put in 20% there. That's a reasonable value for cutting edge modules. Bifacial cell adjustment factor, I'm going to leave that at 0. That is, I'm assuming that we're not going to be using modules that are collecting light on their rear surface. Those are increasingly common. If I thought that I could boost my output by 10 to say 20% using those types of modules, I could put that number in here. We have maximum power point tracking versus clamped operation. This essentially is saying between the battery and the photovoltaic array, do you have a direct connection, or is there a box of power electronics that decouples the voltage of the two such that we can be operating the photovoltaic array at its optimal voltage regardless of what the battery voltage is doing? And that is typical, particularly for larger systems such as this one. And then miscellaneous losses here. This refers to losses other than those stemming from, say, high temperatures or direct clamped operation of the array. So things like mismatch of modules, snow or dust on the modules, wiring losses, things like that. If we look at help, we can see that, typically these values range from a few percent to 15%. I'm not going to be particularly optimistic. I'm going to put in 15%, thinking there might be a fair bit of snow accumulation at this off-grid site. There could also be shading. Now that we've done that, we have essentially filled out all the parameters other than the costs and the power capacity. So let's just, by trial and error, pick a power capacity that achieves a reasonable fraction of the load delivered. So I'm going to guess. I'm going to start off with 2 kilowatts as the size of my array. And I see that in summertime that would be sufficient to meet our entire load all the time. But in wintertime we would fall short. So let's use a bigger array. Let's try, say, 4 kilowatts. 4 kilowatts is sufficient to meet the load almost all the time. Maybe we could get away with a slightly smaller array. So I'll try, say, 3.5 kilowatts. We see that, we can see a slight change here during January, November, and December. Some very small fraction of the load might not be met, but most of the time it's sufficient. So I'm going to use 3.5 kilowatts as the size of the array here. And that's going to be sufficient almost all the time. So that leads to a capacity factor of 7.1%. Of course, that's much lower than the capacity factor for an on-grid system, because during summertime this system is going to be generating a lot of power that maybe we can't use. So it's just essentially discarded. We next want to specify the initial costs of the array. So I click here and I go to the cost database, and I see that costs for photovoltaic arrays, including the inverter, let's see, at this range, including the inverter, might be around, say, $2,000 US per kilowatt. If you think that's too high for your area or too low, use what information you have. You can go to installers and ask them for quotations. But if you don't have that information, this cost database, as I mentioned earlier, is a good first source of information. So I'm going to put in $2,000 US per kilowatt here, and that leads to initial cost for the array of $7,000. There's an argument that I should reduce that cost because it includes an inverter, and I've already included the inverter cost elsewhere. I'm being a bit conservative here, and I'm going to leave that in. For O&M costs here, I'm going to assume that there's very little that needs to be done here that the homeowner couldn't do, him or herself. The batteries don't require a lot of maintenance. They will need to be replaced after 10 to 15 years, but they don't need regular maintenance. Similarly for the array, there's not a lot you can do. If something breaks, it'll need to be replaced, but that's a pretty low probability. And we don't have any of the administrative charges that might be associated, for instance, with an on-grid system. We don't have land rental. We don't necessarily have even insurance costs. If we did, we could include those here. So I'm going to leave that at 0. And if you disagree with that, that's fine. You can put in whatever you think is a reasonable estimate. Now at the bottom here we see this warning sign that the peak system is required. That's because this base load system, this photovoltaic system, is not meeting absolutely 100% of the load. This is just being rounded to 100%, but obviously for some very small percentage of the year this is not fully meeting the load. So red screen is warning us, if you want to meet the load 100% of the time, you should add a peak load system here, which in this case would probably be a genset. However, our assumption is the residents of the home can adjust their behavior such that if they see the battery running down, maybe they don't run the vacuum cleaner, maybe they don't do the dishwasher that particular day, and therefore it's not a problem. So I am going to ignore these warnings and just assume that this is acceptable. We can then go to the system summary. That's the last element of this energy tab. Our photovoltaic system has a capacity of 3.5 kilowatts and it delivers 2,189 kilowatt hours per year. There's a summary of the size of the inverter and the battery there. We also see the fuel savings. So in the base case, there is number 2 diesel being used, 196 gallons per year. In the next video, we will leave the energy tab and go to the cost tab.